So we will look at a numerical which is based on balancing of multi-cylinder engines, inline engines. So here it is given a 4-cylinder engine with two outer cranks which is set at 120 degrees apart and their reciprocating masses each of 400 kg. So that means four of the cylinders and each of the cylinders having reciprocating masses 400 kg. And the distance between the planes of rotation of adjacent cranks is 400 mm, 700 mm and 500 mm respectively. So, and if the engine is to be in complete primary balance, find the reciprocating mass and the relative angular position of each of the inner cranks. That means if we order it from 1, 2, 3, 4, then we have to find 2 and 3 masses and their angular position. And if the length of each crank, that is radius, is given 350 and length of cutting rod is given as L is equal to 1.7 meters and N RPM 500. And we also have to find out what is the secondary mass. So first write what is given. So two outer masses M1 and M4. Since it is 4-cylinder engine, outer masses will be M1 and M4, and that is given as 400 kilogram. And M2 is to be found out. M3 is to be found out, and theta 2 again is to be found out, and theta 3, that is corresponding to mass 3, is to be found out. And what is given? R is given as 350 mm, that is equal to 0.35 meters in SI units, and L is given as 1.7 m, that is meters, and also given N is equal to 500 rpm. So we need to convert it into omega, that is radians per second. That will come, which is 2 pi n divided by 60, and you substitute 500 for n, you will get 52.35 radians per second. So these are the given datas, and L is given to find out, and L is given to find out N, which is equal to L by R obliquity ratio. That is why it is the requirement of L. Other than that, there is no relevance for L. And to draw the planar diagram of the planes, we can draw the same procedure as that we did for rotating masses. So a horizontal line. So starting from first two outer masses, two outer cranks, 1 and 2, and from first crank it is given that it is 400 mm, so if I divide it into, this will be 0.4 meters, and there will be the first inner crank or the second crank, and again next one is 0.7 meters, 0.7 or 700 mm, there will be the second inner crank or the third crank. Let's draw it here. You should not go for scaling. This is just a rough drawing to show the diagram, and the last one is given as 500 mm here, 400, 700 and 500. So 500 means 0.5. So let's name it as 1, 2, 3 and 4. And since we need to find out 2 and 3 masses and angular position like we did in rotating masses, it is better to choose a reference plane here itself. I'm choosing 2. You know why it is choosing, for obvious reasons, to avoid the additional negatives. If you choose 3, you will get 1 and 2 as negative lengths for calculating couples, and if you choose 2, only 1 will be negative. So this is the reference plane, and this will be negative, and in this direction will be positive length when we take couples. So this is the diagram. Now we should construct a table like what we have done for rotating masses. So to construct the table like we have done for rotating masses, there will be two additional columns, that is One is for notating primary crank position, that will be equal to theta, and the other one will be secondary. Okay, I'll write secondary, that will be better. Secondary crank position, that will be 2 theta. Like we have earlier demonstrated that secondary crank will be at 2 theta angle compared to the primary crank, which is at theta. So now naming the plane, we will just name the plane as 1, 2, 3, 4. So first one, plane 1, plane 2, which is our reference plane. So you should denote this as a reference plane. So the distance from the reference plane will be 0, and plane 3 and plane 4. And mass of the first plane is given, that is 400, and mass of the last plane is given. So m1 equal to 400 and m4 is equal to 400, and we need to find m2 and m3, and the radius is given. All the cranks are at a radius 350 mm or 3.350. So 0.35, 0.35 and 0.35. And the centrifugal force will be the product of radius and the mass, that is centrifugal force divided by omega square, since all the cranks are rotating at same angular velocity. So it will be 400 times 350 will be 140, and since m2 is not known, we can write 350 m2, and similarly here 350 times m3, and again the last one will be 140. And to take the reference plane, distance from the reference plane, we can refer to the plane diagram. Since 2 is our reference plane and 1 is left of 2, we will take negative, and the distance is given 0.4 meters. So it will be negative 0.4, and third one will be positive 0.7, and last one will be 0.7 plus 0.5. So this one will be 0.7, and this one will be 1.2, that is 0.7 plus 0.5. And the couple we can get by multiplying mr into L. So that will be negative 56, 140 into 0.4. And since 2 is the reference plane, there will not be any couple acting. This one will be 0.350 times 0.77 times m3. That will be 0.245 m3. And last one will be 168. 1.2 times 140 will be 168. And here it is given that two outer cranks are at a radius 120. So that means 1 and 4 is at an angle 120. So if you fix 1 as the horizontal, so that will be 0 degree. So the fourth crank, that is outer crank, will be 120 degree. And we don't know the angular position of second and third, so we should find it theta 1, 2 and theta 3. That is to be found out. And we know secondary crank will be at a position double the angle of the primary crank. So first one is 0, so that will be 0, 2 theta. This will be 2 theta 2. When we find theta 2, we can multiply by 2 and find out that 2 theta 3. Again, after determining 2, 3 theta 3, the theta 3 we can multiply it with 2, and last one will be 240. So this is the table which contains all the data we require to do. And the procedure is same as the procedure we adopted for rotating masses. First we will draw the couple diagram and find this 0.2545 into M3, and from that we will find M3. And we will substitute it in this one, and we will do the force polygon, and we will closing side of that will give you the 0.35 into M2, and we will get M2. and from here we will get theta 3, and from here we will get theta 2. So I will just show you how the force polygon will come. Okay, so first couple polygon, we will start with one which is negative, so take it for an appropriate scale. I'm not scaling here, but you should draw it according to a scale, and since it's negative 56, we will take it as the left side, so negative 56, and the only crank position we know is the 168 couple, that is for the outer crank, which is at a 120 degree. We will draw first the primary couple diagram and force diagram, which is at theta degrees, then we will go for secondary couple diagram. So now we are drawing primary couple diagram, so I'll just give the name primary couple diagram or polygon, whatever you can call it. Primary couple, okay, I will call it as polygon, couple polygon. So this is 56, 56, and from that we will take this 168, which is at 120 degrees for primary couples, that is 120 degrees. So you can use a protractor and place your protractor at this end and take the 120 from the outside. So 120 will be somewhere around, sorry, since it is negative we should take the angle from here. So 120 will be around, yeah, here. So this will be 120. Since it is a negative couple, we should take the inside angle. So 120 line, which is equal to 168. So it will be 168. This will be couple 168. We should scale it up accordingly. And the closing side, since already there is three sides for this, negative 56.245 into M3 and 160, this closing side will give you the 0.245 into M3. So if you can take that scaling accordingly, you will get this as the closing side, and this will be your 0.245 M3, and that will come, if you scale it and rescale it properly, you will get 0.245 M3 equal to 196 kilogram meter square, and you will get M3 is equal to 800 kilogram. And if you want to take angular position of it, since this is taken as negative, you should take the angle from the horizontal, and that angle should be taken like this. Because this is negative, the angle with respect to this horizontal will be this one, and it will come at around, if you do it properly, this will be theta 3, and if you draw it according to the scale and with clear good accuracy, you will get theta 3 is equal to 318 degree. So that is primary force, primary couple polygon, and you got M3. So you can substitute this M3 in this one, and you will get around 280. This will give you 280 kilogram meter, and we already know the angle 318, so we can draw this force polygon, primary force polygon with angles, and find out 0.350 m2 as the closing side of that polygon. So this will be 280. I'm just erasing it from the table. Keep in mind that is 280. So force due to, or force acting on plane 3, you can write it as force in plane 3, that is M3 into R, that will be equal to 280 kilogram meter. So you can use it for drawing primary primary force polygon. So you will draw primary force polygon. So for drawing primary force polygon, these are the forces: 140.35 into M2. This has to be found out, but this we already got as 280 because we got M3 from this one, and we also got theta 3 as 318. So and 140. So we got 4 sides, and 3 sides and 3 angles are known. So we can draw a polygon. So first is we should draw 140, that is positive. So take it to appropriate scale and draw 140. This will be 140 force, and from there you should draw 120 degrees with another 140. If you draw another 140 at 120 degrees, from here the 120 will be, you can draw it two ways. You can draw it either above or below. So I am going to draw it below, placing the protractor. So we have drawn 140, which is the primary force associated with the first plane. So second one is unknown. We can draw the third one. We know the angle as 318. So from here, if you place a protractor to take 318, which will be 180 plus how much? That will be 180 plus 138. So this will be 180, and if you can draw a 138, take a 138 from there, then you will get exactly 318. So 180 plus 90 will give you 270, and 270 plus a 48 will give you, so if we can rotate it to here, and another 48 will give you 398, 318. So from here to 48, so 180 plus 138, so okay, you will get a angle which resembles, or the line which resembles around here. So this will be your 280 line, 280, and from again here you take another 120, which is for 1/4 plane, that is 40, and that will resemble, if you take the angles properly, you will get a side like this, and this will be your another 140. So make it look like a 140. Okay, this will be another 140, that is for plane 4. This will be for plane 4, this will be for plane 3, this will be for plane 1, and the closing side will give you the primary unbalanced force, which is caused by, not unbalanced force, the remaining force, which is this one, and that will give you 0.35 into M2. So if you draw it properly, this 0.35 into M2 will be measured and scaled as 0.35 M2 will be 294 kilogram meter, and M2 you will get as 840 kilogram, and also, and if you take a horizontal line here and take an angle, you will get an angle equal to, that is theta 2 will be equal to 165 degree. So we have completed the first part of the question, that is to find angular position of each of the inner cranks and the reciprocating masses. So this is found out. Now we want to find out what is the maximum secondary unbalanced force. To draw the secondary unbalanced force, we need to complete that table. We already got this as 168, this as 318. So 2 times this will be 318 will be 636, but 636 we cannot draw, so we will do it. 636 will be taken as 360 minus 636 when we draw it, because 636 will be 360 one rotation and the remaining angle, and this will be 168. So double of that 168, that will be 120 plus 16, so 136. 136 will be the, sorry, 236 will be the angle. So this will be 236 and this will be 636, but 636 will be taken 360 minus 636, or 636 minus 360. Okay, so let's move on to drawing secondary polygon, or the secondary for force polygon, to find out the unbalanced. So moving on with the secondary force polygon to find out the secondary unbalanced force. So secondary force polygon. So the forces magnitude will remain the same as these primary forces. Only thing is the angular position will be changing. So taking 140 as the first force, so we will draw according to the scale an angle. Sorry, I'll have force of 140. Take it to appropriate scale. Since it is positive, drawn towards right. Then second one is at an angle 236. You see that this is 236. This is not at 168, it is at 236. So to draw the secondary polygon, force polygon, so 140 is drawn. Now we have found out M2, and if you substitute that M2 into here, you will get this as 294 kilogram meter. You found out M2 from the force polygon of primary force polygon. So substitute that M2 here, and that will get you 294. So that 294 is taken at an angle 236. So 236 degree, because we are taking a secondary force polygon, so 236, and if you place your protractor, 236 will be 180 plus another 56. So it will come out around, if you place it again here, another 56 you have to take, 180 plus 56, so it will come at around here 236. So this will be that line, and that should be scaled to the 294. So you will scale, you should scale it to 294. I'm not scaling, but you should scale it to 294. Then the third one will be at an angle 636. 636 you can take it as 636 minus 360. 636 minus 360. How much it will be? It will be 276, if I'm not mistaken. So you should take that angle as 276 degree from this end, and the force we already found out M2. So if you substitute in this, you will get it as 280 kilogram meter. So 280 with the secondary angle, that is 636. 636 is drawn as 360 minus 636, so it will come at around 276. So 276 from here. So how would you draw 276 from here? It will come, 270 is directly below, that is 190 plus 180 is 270, so you should take this 180 plus another 96. So if you take a 96 by placing the protractor correctly at 180, this 96 will give you 276. So and 276 is equal to 280 kilogram meter. So taking that line at 286, sorry, 276, so this should give you a 276, and that should be scaled to 280. And this closing side, so not closing side, one more angle is here, that is the 140 angle, so 140 force, and that is at a 240 degree with respect to the horizontal. So we should draw that also, then you will get a force. This should be another force, that is 140 at an angle 240 degree. 140 force at an angle, secondary couple will be secondary force will be at 240 degree. So you're taking 240 from here, so you will get a 240. If you take it properly, you will get something that resembles like this, and you should take 240 as 180 plus another. If you place your protractor here, 180 plus another 60 you should take. So 60 should give you 180 plus 60 should give you 260. So that will be the secondary force polygon, and that secondary force polygon, these are the four sides of the secondary force polygon, and since it is not closed diagram, this is an unbalanced polygon. So to find that unbalanced force, you just join the endpoints of the beginning and the last force, and this will give you the secondary unbalanced force, which is to be found out. This is not representing at any point, this is actually inherently unbalanced. So this is the secondary unbalanced force. So since the secondary force polygon is not closing, that means the secondary force is unbalanced. So the secondary unbalanced force, we know it as secondary force is equal to mr omega square cos 2 theta divided by n. What we got here is mr omega square. If you do measure it and scale it, you will get it as, actually you will get it as 4.7 into 4. If I have scaled, used a scale of 1 is to 4.7, so I will tell you. And if you have scaled it in a correctly, you will get it as 658, sorry, 658 kilogram meter. This only represents mr, and the angle cos theta is taken, so mr cos 2 theta this is representing. So to get the total unbalanced force, fs unbalanced, it will be 658 times omega square and this n. This is not included now because we have divided it with omega square to find out the force, and n is not included. So omega square divided by n, that will be 658 times omega square, we have already found out that as 52.35 earlier, 52.35 square divided by n. N can be found out by L into R. So if you do it properly, you will get Fs unbalanced as 371.2 kilonewton. This will be the unbalanced secondary force. This you measure it, you will and scale it, you will get it as 658 kilogram meters. Multiply it with omega square n to compensate for the equation fs omega square n cos 2 theta by n. Cos 2 theta is already included in this because we are taking angle as 2 theta, and we have to multiply with omega square by divided by n. N is L into R, sorry, L divided by R obliquity ratio. So if you multiply this with omega square by n, you will get answer 371.2 kilonewton. That is your answer for the third part, which is maximum secondary unbalanced force. This is 371.2 kilonewton. So this is how you solve it. It's a lengthy process and you should do it with accuracy. Just to brief the process what we are doing, first consider this table, take couple polygon of primary forces, that is the angular position is taken as theta, find m3 and theta 3, then substitute it in the force polygon and you will get m3, then draw the primary force polygon, find m2 and theta 2, then you have found out all the m2, m3 and theta 3. Now draw the secondary polygon, that will be a open polygon, so close that polygon with a straight line and measure that straight line and scale it. You will get it as 658 kilogram meter. Multiply it with omega square n to compensate for the force, secondary force equation, that is mr omega square cos 2 theta divided by n. So cos 2 theta is already included, mr is also included because force is taken as mr here. So mr into cos theta is multiplied with omega square n, and we are taking maximum. So cos 2 theta maximum will be 1. That is why we are taking only multiplying with omega square divided by n. So if it is cos 2 theta is maximum, that means that will be 1. So we maximum will be mr omega square n. So cos 2 theta will be equal to 1 for maximum condition. So mr omega square by n is the maximum secondary force. So we multiply with omega square n, you will get it 371.2 kilonewton.